Hello everybody. In this video we're going to start with the addition of minor losses to the pipes in Aspen Plus and see how the inputs will be and how we can compare the results that we can get manually with the results that we can get from Aspen Plus so that we can understand how the calculations are going. So what I'm going to do is I'm going to take one of these pipes and see where we can get these fittings or the sources of minor losses can be entered into the software. So here, if we check what we can put as inputs, this is something that we have already checked before. Here we put the pipe dimensions, the length, the diameter, and the elevation, if there's any elevation, the pipe roughness. And this is the part where we put the important information, the information that the software will not run the simulation without having this information entered to the software. And here in the thermal specifications, we have talked about the either we are going to go with constant temperature or we'll have heat transfer between the pipe and the surroundings, and we have already talked about this as well. The point or the place where we're gonna put the minor losses or the sources of minor losses are gonna be in the fittings 1 and fittings 2. And to understand why we have two places to put the sources of minor losses, we just need to understand that the sources of minor losses are, if we kind of go back here and check this slide, we said that it can be valve, or it can be fittings, or it can be entrance or exit flow, or expansion and contraction. These two sources are the parts that are connected to the pipes. So you have to do some connection between the valve and between the fittings to the pipe so that you can get them part of the system. And that's why we mentioned at the end of the last video that there are two types of connections, the flanged and the threaded connections. So these are for the fittings and for the valves. But for the entrance and exit flow, for the expansion and contraction, we do not have this issue. And this is what happens here. In the fittings 1, it's concerned with the sources of the minor losses that require connections. And that's why we have in the beginning, is it flanged or screwed? This is the reason why we have them here in a separate part. We have here what we call the gate valve or the butterfly valve. You have different types of valves in the elbows. You have the T's and the branched T's, and you can here put the number of parts that you want. So let's say I have one gate valve and I have 190 degrees elbow, one straight T, whatever the number. You can have two branched T's. It doesn't matter. This is gonna be at the end of the day, they're gonna be converted into K's. So this is 1K for the gate valve, 1K for the 90 degrees elbow, 1 for the straight T's, and 2 for the branched T's. It's gonna be all added together and put in the minor losses term, as we mentioned in the previous video. So this is how we can define this. This is for the first part. This is what we have here. I'm just gonna do a very simple run now, and I'm gonna see what results we're gonna get. And it's now doing the simulation. Now the results are done, so you can check the results, and here you'd see that this is the total pressure drop. There is no elevation pressure drop. And the point that I want to highlight is the equivalent length. And to understand what we mean by the equivalent length, I need to go here to define what we mean by the equivalent length. So we mentioned that there are two sources of the losses, the major and the minor losses, and we mentioned that this can be calculated from this equation, and this is minor losses can be calculated from this equation. In some cases, people would like to express the losses as in terms of length. So I would like to know what will be the length of the pipe that would generate the losses equivalent to the sum of these two losses. So I want to convert this into a shape like this with a length which would be whatever the value of the length. It's good to know this equivalent length because it gives us a feeling of the percent increase in the pressure drop or in the losses. So I know that these losses are caused by 10 meters, and I would know with the equivalent length that this is equivalent to 50 centimeters, to 1 meter, 2 meter, 3 meters. So this is gonna give me a good feeling of the of the minor losses compared to the major losses. So the way we calculate the equivalent length is that, as I mentioned, we do the summation of these two, and we say this is equivalent to the losses caused by, or the major losses caused by, the equivalent length. And with simple simplifications, we cancel out the v squared over 2g, and then the equation will end up like this. The equivalent length is the initial length, or the total, the actual length, plus the summation of the k's multiplied by d over f dash. If we don't have any minor losses, the k would be 0, and the equivalent length would be the actual length, which is what we should expect. So in this case, we have the actual length, as we put in the setup, is 10.73 meters, and here in the equivalent length we see that it is 10.92 or 0.925 or 23. Which means that there is some increase in the losses due to the presence of a minor loss. And I can tell simply from the equivalent length that this is a very small increase in the losses, because it was 10.73 and now it's 10.92, so it's almost 0.2 meters losses or 0.2 meters increase in the length of the pipe. One thing that I would like to do is to compare what we got from here with what we can get from the manual calculations, as I did in the previous videos. So I here have one source of losses, which is one gate valve, and if you remember, we had these tables before, and we have here the gate valve. There are some cases for the gate valve, and we have this is 0.15, and if it's kind of quarter closed, it's higher, but I'm gonna go for the 0.15 now. And I have my Excel file here. I added some parts for the minor losses, and here where I can calculate the equivalent length, and I would just put the k of 0.15, and it's getting the equivalent length 10.84. Which is very close. It's here 10.93. So it's not a lot of, or it's not a big difference. It's 0.93, and here what I got 10.83. Sometimes there are some change or differences between the values in the tables and the values in Aspen Plus. Again, it's not going to be a big difference, but it may be a source of some errors or differences in the calculations. So this is how we can put the valves and this stuff. But you can face some issues while working with this. Like in the case that we were working, we used a fully open gate valve. But if I have, let's say, quarter closed or half closed, I cannot find it here. It just tells me that it's a gate valve, not more than that. And in such cases, Aspen Plus gives me the option to define what it calls miscellaneous sources of minor losses. You can define it either by what we call the equivalent length, which is how much length to the diameter. It's 1 time, 2 times, 3 times the diameter. If I know this ratio, then I can put a number here. Or by the k. So let's say I'm gonna put the k here as 0.15, just to check what I'm get. I can just say that it is a gate valve. Let's make it half closed. Oh, this doesn't give me a lot of space. I'm just gonna keep it half closed, and the half closed is 2.1. So I'm gonna put this as 2.1, and I'm running the simulation now and getting the results. The equivalent length now is 12.26. If I put it here as 2.1, it's 12.26. So it's giving exactly the same value while defining the k's from the miscellaneous k factor. again, you can, if you know what the losses will be equivalent to, how much length of the pipe, you can put it like this. What I know that it's the data that are available are mainly K values, so it's going to be easier to work with these. So this is the first part where we can put the minor losses. The second part is the fittings 2, which is concerned with the entrance and exit flow, expansion and contraction. And here you see that this gives us like some options, either to go for none, so I'm not gonna consider this entrance flow. Again, just with a quick review on what we mentioned in the last video, that the entrance and exit flow, where was it? Yeah, you can ignore it in if the length is more than 10 times the diameter. So Aspen Plus gives you the option either to consider it or not. Here you can see what we can, it's called inward or flush. And actually this is not something that I knew about before, and I tried to find some information about it, but I couldn't find a lot in the textbooks and in the internet. But it was one thing that I tried, is to search the help. So if you are trying to find some information about a place where you're trying to put some inputs, you can just press on F1 button, and it's gonna open the help related to this. So it's kind of very handy. But the problem with the Aspen Plus help, that the information that are provided by the help are very, very small information, like very little information. So it tells you that use this sheet to specify the fittings at the pipe entrance, a sudden enlargement or contraction, and orifice plate, which is what we know actually. It doesn't give you any information about the what's called flush or inward. It tells you that the amount that depends on the entrance bend R over D for a flush entrance. So based on this, what I found in my search, that the what it calls the flush is to have the entrance kind of welded, rounded welded entrance. So you have here this radius here, and this is the diameter. That's why it asks for the ratio between the R and D. So I believe that this is what it calls the flush. Please correct me if I'm wrong, but this is the best I could find. And in the inner flow, what it calls an inner flow is the 90 degrees inlet, where there is no radius here. So this is what it calls the inward and the flush. So in the flush, you need to provide the R over D ratio for any value from this list, or to keep it inward, and in this case you don't need to provide any more information, and none, it's not going to consider the entrance flow at all. What we call here pipe exit, it can account for the pipe exit if I click on this or check this box. I'm not gonna do that now. And here it tells you the enlargement and contraction, and here it asks you to, of course, just to make it simple for you, the software tells you a hint that you put or define the value. It's not showing up for, yeah, it's the diameter of the smaller pipe if the fitting is at the beginning, or the larger pipe if the fitting is at the end of the pipe. In a simpler way, define the diameter of the other pipe. So you know the diameter of your pipe, either it is the diameter of the other pipe if it's in the beginning, because it's going to be an expansion, so the pipe going in the inlet should be smaller, or the exit pipe or the outlet pipe should be larger, so you have to define this. And the other way, in the contraction, it's going to be the same. And the angle, we mentioned the angle before for the expansion and contraction, which is this angle theta. You need to define it because it affects the losses. The orifice is kind of one thing that is put connected to the pipe for flow measurement calculations, or for the sake of measuring the flow. And it's just a disc that is connected to the pipe. I think it was in the, no, it's not in the help. It's just a disc that's put with a smaller diameter. It makes like a contraction in the flow and then expansion after that. So you just need to define the diameter and the thickness of the orifice. So these are all the information that you can put here. to account for the minor losses. I think this should be good enough for whoever wants to work with the minor losses in Aspen Plus. In the next video, you will see more information about the losses. If you want to define more information about the valve, we can go through this by adding a valve to the stream. So this is going to be the topic of the next video, inshallah. So I'll see you then. Goodbye.